Hello everyone, and welcome back to some more remote learning. In today's video, we're going to go over the basic derivative rules. So as I mentioned in the previous video, taking the limit of the slope of the secant line may be very tedious, especially when working with polynomials with large degrees or complicated functions. However, there are derivative rules that remove the need to even take the limit, making the derivative a lot easier to calculate. So let's go through a couple of those basic rules now. The first one is going to be the constant rule. Essentially, what the constant rule is if we have some number c, and I'm going to say that c is in the real numbers. So this symbol represents is in, and this r means the real numbers. So c is some real number. Then if we take the derivative d dx, taking the derivative of c, that's going to be 0. So looking at the two examples provided, we're going to take the derivative d dx of 3, taking the derivative with respect to x of a constant, according to our rule, is 0. And here we have it. If our function f of x is equal to -1/4 is just a real number, so that derivative f prime of x is going to also be 0. This is one of the very simple basic differentiation rules. Let's move on to the power rule. Now the power rule is a little bit more complicated, but it's used a lot, so just keep practicing and you'll get the hang of it. The power rule says that if we're trying to take the derivative with respect to x of some x variable to the power of p, where p is in the real numbers as well, so we're going to bring that exponent down in front and then multiply it by that variable x to the power of p minus 1. So again, for the power rule, you drop that exponent of p down in front so that it's now multiplied, and then we have x to our new exponent is p minus 1. So let's take a look at this derivative x squared. Dropping our exponent down in front, we'll have 2, and then we multiply that by x to the 2 minus 1. P times x to the p minus 1, you'll see that this simplifies down to 2x to the, well, 2 minus 1 is 1, so 2x to the first, which is 2x. Now our second example for this is if our function is x to the fifth, then the derivative f prime of x is going to be, bring that exponent down in front, 5x to our new exponent, that power minus 1. So this becomes 5x to the fourth. Next we move on to our constant multiple rule. And again, this constant multiple rule is going to deal with some number c that's in the real numbers. So if we take the derivative of some real number c times our function f of x, then we can simply pull that c out in front, so that coefficient of our function out in front, and then take the derivative of f of x. So that c will just be multiplied by whatever you get for the derivative of f of x. So this is c times f prime of x. So let's look at this first example. If we have -4x, I'll rewrite this as -4 times the derivative of x. Now this is like the power rule. If you can envision x being raised to the first, if I bring that 1 down in front, we have 1 times x to the 1 minus 1. 1 times x to the 1 minus 1, well, that's equal to 1x to the 0. And we know that x to the 0 is 1, so anytime we have the derivative of our variable and it's raised to the first power, that's just going to be 1. So we'll have -4 times the derivative of our function, which is 1, and that's going to be -4. Now let's look at f of x equals 3x squared over 2. I have that 3 halves multiplied by everything. So I'm going to rewrite this as 3 halves times, now we're going to take that derivative of our x squared. So this is going to become 3/2, that coefficient all the way out in front, times the derivative of x squared. Remember that power rule. We bring that exponent down in front and multiply it by x to that exponent minus 1. So 2 minus 1 gives us 1, so that's just 2x. And now we do a little bit of algebra to simplify the problem. 2 cancels out with 2 to give us 3x. So the derivative of 3x squared over 2, when I used that constant multiple rule and pulled that constant that was multiplied by everything out in front, it just became 3x. And lastly, the rule that we're going to go over in this worksheet is going to be the sum rule. So if I'm taking the derivative with respect to x of my function f of x plus my function g of x, well, similar to the limit rule, I can just take the derivative of each and add those derivatives together. So this is going to be equal to the derivative of f of x plus the derivative of g of x. And I wrote a little big there, so sorry about having to squeeze that all in, but we have the derivative of f of x plus that derivative of our function g of x. How this rule works, let's try it out in this first example. So I'm going to split my derivatives up and take the derivative of x cubed and add that to the derivative of 7x. The derivative of x cubed, well, we're going to have to use our power rule. So we bring that exponent of 3 down in front, and then it will be x to the 3 minus 1. X to the 3 minus 1 is x squared. That's that first derivative, and we add it to the second derivative, the derivative of 7x. In this case, we're going to use the constant multiple for that derivative. Pull that 7 out in front, and the derivative of x is just 1. So 7 times 1 gives us 7. Lastly, we're going to look at f of x equals 5x to the 4th minus 2x. Then, what exactly is f prime of x? And I want to make a note that the sum rule, we can think of this subtraction as adding a negative. So we're going to be taking the derivative of our first function, which is 5x to the 4th, and then we're going to be adding that to the opposite of the derivative we get with 2x. Or feel free to bring that negative within that derivative. So as opposed to adding, I'll just subtract that derivative of 2x. The derivative of 5x to the 4th, this is a mix of the power rule and the constant multiple rule. We have that 5 out in front, so we'll do 5 times then that power rule, 4x to the 4 minus 1, which is 4x cubed. And then we'll subtract the derivative of 2x. Constant multiple rule, bringing that 2 out in front and multiplying it by the derivative of x is just going to give us 2 times 1, which is 2. Simplifying this, we can combine our 5 and our 4, because 5 times 4 gives us 20, so we have 20x cubed minus 2. And that's the derivative for that last part in our example for the sum rule. Now let's apply this in example 1. In example 1, it says, find the equation of the tangent line to the following functions at the given values a. So remember, the tangent line, that slope is equal to the derivative. So in order to create that tangent line, we first need to take the derivative, which will give us an equation for the slope, and then we'll plug in our values of a to get the slope at our exact point. And then we need to also find that point on the function that our tangent line intersects in order to form the line. So I think right off the bat, it's good to start by just taking the derivative of the function, because that is our equation for the slope of the tangent line. So taking the derivative of, let me go ahead and zoom in, taking the derivative of f of x, which is equal to 3x squared plus 4, that's going to be, well, f prime of x is going to equal that constant multiple, leave that 3 out in front, and then we're going to take the derivative of x squared, which is 2x to the 2 minus 1, or 2x to the first, 2x, plus the derivative of 4. 4 is a constant, so that's going to be 0. So our function's derivative is 3 times 2, which is 6 x. So that's the derivative, and again, the derivative gives us the slope of the tangent line. So if I want to find the tangent line at our first point, a equals -3, well, again, to get that tangent line, I need the slope and a point. So if my x value in this case is -3, I'm going to plug that right on in to find the slope at -3. So when a equals -3, I'm going to do f prime of -3. That's my slope to get 6 times -3, which gives me a -18. So my slope is -18 when a is equal to -3. But now I need to also find a point on my line. And how do I find a point on my line? Well, I've already got that x value. I just need to plug that into my original equation to also get the y value. So f of -3 is going to be 3 times -3 squared plus 4. So again, I'm going to label, here is my slope, and this is going to be my y value of my point. -3 squared is 9. 9 times 3 is 27. 27 plus 4 is going to give me 31. So my point is -3, 31. So the equation of our tangent line, we'll use point slope form. Y minus y1 equals m, our slope, times x minus x1. So I'll have y minus 31 equals our slope of -18 times x minus a -3, so x plus 3. And there's my equation of my tangent line when a equals a -3. Now we're going to go through those same exact steps, except we're going to do it when a equals a +1. I already found my derivative or my equation for my slope, so I don't need to go through that process again. I'll just find the point associated when x equals 1, and I'll find the derivative associated with when x equals 1. So when I have an a value equal to 1, let's start with our function value to get the point first. F of 1, plugging 1 into my function, that's going to be 3 times 1 squared plus 4. 3 times 1 squared is 3, plus 4 gives me 7. So my point that I'm going to work with for my equation is 1, 7. Now, finding that derivative in order to find my slope at the point 1, I'll take f prime of 1, which is going to be 6 times 1, which equals 6. So 6 is my slope. And then I have a point. Let's just write this in point slope form. No need to write it necessarily as y equals mx plus b. That's just the algebra part. So if you want to write it like that, I'll let you do that on your own. But now we have y minus 7 equals our slope m of 6 times x minus 1. And that's our equation of the tangent line when x equals 1. Our a value is 1. Let's do one other example with finding the equation of a tangent line in part B. Our function is y equals 5x cubed plus 6x squared minus 8x. What we're doing is we're going to take the derivative with respect to x. That's our equation for the slope of the tangent line, the derivative. Now note here, as opposed to having f of x, I say that my function value is y equals something. So we can either write this as y prime, or we can write it as dy dx. How I get that dy dx, I mentioned in that previous video, but if you can envision taking the derivative with respect to x, that y remains with the d in my numerator, dy dx. This also is equivalent to if we were to say f prime of x or y prime. Just note that dy dx is taking the derivative of our function y with respect to x. So dy dx, using this notation, is going to equal constant multiple rule. I have my 5 out in front, then I multiply by 3, bringing that power down, x to the 3 minus 1, which is 3x squared. Then I'm going to add that to, again with the constant multiple rule and the power rule, 6 times 2x. And then lastly, I'm going to subtract, pulling that 8 out in front, that would be an 8 times 1. Simplifying this down, we'll get 15x squared plus 12x minus 8. Now to make the tangent line, I need the point where I'm trying to find the tangent line, and I need the slope at that tangent line. So using my x value of 0, I'm going to start by finding that point. So I know that I have 0, comma, f of 0, or essentially plugging in 0 for x. So y is going to equal 5 times 0 cubed plus 6 times 0 squared minus 8 times 0. It's fairly silly to write this all out because 0 is multiplied by everything, which gives me 0. So my point that I'm finding the tangent line of is the point 0, 0 on my function. Now I just need to plug in 0 into my derivative to figure out what my slope is. So into dy dx, I'm plugging in my x value or a value of 0. So my derivative function here, I'll have 15 times 0 squared plus 12 times 0 minus 8. That's going to equal a negative 8. So my slope is negative 8. I have my point 0, 0. So I'll have y minus 0 equals negative 8 times x minus 0, which, simplifying this one down, since it's fairly easy to simplify, will give us y equals negative 8x. So my tangent line at my point 0, 0 is y equals negative 8x. Now quickly, before we move on to just practicing taking the derivative, I want to think about something that you may be asked to solve for, and that may be a horizontal tangent line. So if you're ever asked to find the horizontal tangent line, think about the slope of a horizontal line. That slope would be 0. So in either part A or part B, you could have been asked to find the equation of the horizontal tangent line. So you would see when that derivative equals 0. So in the case of example A, because A is going to be a little bit easier to visualize than B, when this derivative, which is 6x, when does that equal 0? That's when x equals 0. So when we're at 0 in the x, we have a horizontal tangent line, meaning that our tangent line has a slope of 0. But you continue calculating that tangent line the same way. You know the slope is 0, so you just have to find that point that makes the slope 0, and then write your equation of the tangent line. So like I said, let's move on to just practicing taking the derivative. So we're going to be evaluating the following. So in part A, we're taking the derivative with respect to x of x cubed plus x squared plus x. That's going to be, well, the derivative of x cubed is 3x to the 3 minus 1, which is 3x squared, plus the derivative of x squared is 2x, plus the derivative of x to the first, bring that exponent down, 1 times x to the 0, which is going to leave us with 1. There we go, 3x squared plus 2x plus 1. Now just to think about this and tie it back to what we did in the previous example video, think about how long this problem would have taken me if I took the limit of f of x plus h minus f of x all over h as h approached 0. This would be fairly tedious, but we just found this derivative in under a minute. Whereas using the limit method, it would take a lot longer. In B, we're taking the derivative with respect to x of pi. Remember, pi is just what? Pi is just a number. It's a number in that set of real numbers. It's a constant. If we take the derivative of the constant, we always get 0. Now in part C, I switch it up a bit just by changing the variable, but we're still taking the derivative with respect to the variable in that function. So we're taking the derivative with respect to t. All the same rules that we do with that variable x still apply. So we're going to start by, well, constant multiple rule. We'll pull that 8 out in front and then multiply it by the derivative of t squared, which is 2t. And then we're going to subtract using that sum rule. Again, constant multiple rule, pull that 7 out in front. The derivative of t is just 1, so minus 7 times 1, or minus 7. Simplifying this down, we'll get 16t minus 7 as our solution in part C. So changing up the variable does not change the process. We just have a different variable. Moving on to part D, I'm taking the derivative with respect to x of 3 over x to the 6th. Now we didn't really address having something in the denominator yet. That's going to get addressed when we talk about the quotient rule in the next video. However, because it's just a constant in that numerator and our denominator is just a monomial, so one term, we can write that as a negative exponent in the numerator. So I'm going to rewrite this before I take the derivative as 3x to the negative 6th. And then we'll keep on going with that power rule. First, leaving that 3 out in front because of the constant multiple rule, and then we're going to multiply that by bringing that negative 6 down in front. Then we'll have x to the negative 6 minus 1. We're going further into the negatives. That's going to be to the negative 7th. So this is going to be negative 18x to the negative 7th. And as you guys are probably getting to know me now, I don't like to have negative exponents in my answer. So I'm going to rewrite this as negative 18 over x to the 7th, putting that x to the 7th as a positive exponent in my denominator. Moving on to part E, we're taking the derivative of our function with respect to r. So r is the variable that we're taking the derivative with respect to. So we can use the sum rule, splitting this up at the start, taking the derivative of 3/2. 3/2 is just the constant, so that's going to be 0 plus, what's the derivative of r over 5? That's like 1/5 times r. So if I'm taking the derivative with respect to r of 1/5 times r, constant multiple rule, bringing that 1/5 out in front, the derivative of r is just 1. So this will be 1/5 times 1. So 0 plus 1/5 times 1 is going to give me 1/5. And quickly, just to try to tie everything together to give you different ways to think about this, when we get our derivative to be just a constant, that means the slope is always the same. And what kind of function is 3/2 plus r over 5? That is y equals mx plus b, or in our case, mr plus b, where our slope is 1/5, our variable is r, and our y-intercept is 3/2. So because we just have a line, we should think that the derivative is going to be the same anywhere on that line. So that's where we get, well, the slope of that line is always 1/5. So the derivative is always 1/5. This is just something to think about, a note to make to try to tie different things together. Moving on to F, we have the derivative with respect to x of x to the e. Remember, e is in those real numbers. It's just some power, that's 2.718 and so on. So it's just some decimal. But we treat it the same way with the power rule. We're going to bring that exponent down in front, so e, and that's going to be x to the e minus 1. And we're not going to simplify e minus 1 down because it doesn't really do anything for us. So e times x to the e minus 1 would be the solution for F. E x to the e minus 1. In G, we're taking the derivative with respect to x of 29 to the 5th. I don't care what value 29 to the 5th is because x is not even in there. 29 to the 5th is just a constant. The derivative of a constant is 0. And then lastly, in H, we're now going to take the derivative with respect to y. Again, it doesn't matter which variable we're taking the derivative with respect to, as long as, for now, that's the only variable in our equation. Eventually, you're going to learn how to take the derivative with multiple different variables in the equation, but for now, we're just taking the derivative with respect to y, and y is our variable. So this is going to be, well, power rule at the start. That would be 3, bringing that exponent down, y to the 3 minus 1, so 3y squared, minus constant multiple rule, pulling that 4 out in front, and then we have that power rule, y squared becomes 2y. So we were using that sum rule, and we split this up into 2 separate derivatives, and now we're going to simplify. So we'll have 3y squared minus 4 times 2, which is 8 times y. 3y squared minus 8 y. Now, let's move on to higher order derivatives. So in all of those examples above, we took the derivative only once. We found what's called the first derivative when we take that derivative one time. But what if we want to find the second derivative or third derivative and so on? Well, we can just keep taking the derivative. So if we want to find the second derivative, we're going to take the derivative of our first derivative. So we take our function, take the derivative of that, and then take the derivative again. So let's quickly just go over the notation before we jump into example 2. So we know that the derivative of our function d dx of f of x we write as f prime of x. But if we're taking that derivative of f prime of x, well, then we're going to write that as f double prime of x. Let's say we take the third derivative, then we're going to take the derivative of f double prime of x to get f triple prime of x, the third derivative of f of x. So let's say we continued on, and now we're taking the derivative with respect to x of f, and we took the derivative in minus 1 times already, and we're taking the derivative one more time. We would write that as the nth derivative of x. So really, you can continue on just as long as that n represents those whole numbers, taking the derivative so many times. There's different types of notations besides f of x. We could have also said the derivative of y is y prime. So that second derivative would be y prime prime or y double prime. So for example, y prime, taking the derivative of that would go to y double prime, and so on. Very similar to that function notation. But think about if we're taking the derivative of dy dx. Remember dy dx, that was when we took the derivative of our function y equals something. So the derivative of y with respect to x, if we take the derivative again, we're just going to have the second derivative of y all over the derivative with respect to x with that power of 2. So the second derivative of y with respect to x. So let's go ahead and dive into our example 2 below. We're going to find the nth derivative of the following functions. So in part A, our n value is 3, so we're going to find that third derivative. And in order to find the third derivative, we have to first find the first, and then the second, and then finally the third. So starting with finding the first derivative, f prime of x, that's the first derivative. Using our power rule, that's 3x squared plus 2x goes to 2 when we take the derivative of that. So 3x squared plus 2 is that first derivative. Now if we take the second derivative, f double prime of x, so now we're at an n value of 2, that's going to be, well, the derivative of our first derivative. 3x squared, the derivative of that 3 stays out in front, bringing down that exponent of 2, so that would be 3 times 2x to the 2 minus 1, so 3 times 2 times x, plus, now we have a constant, so that derivative is 0. So our second derivative is 6x. And then finally, if we take our third derivative, f triple prime of x, the derivative of 6x is just going to be 6. So that is our third derivative. If I asked for the fourth derivative, I'd continue on and I would get 0. Well, taking the derivative of 0 is going to continue to give me 0. So if I ask for the ninth derivative, f9, because as we go to larger numbers, we don't continue on with those tallies. So the ninth derivative of f of x would be 0. Once we go to the fourth derivative, we get 0, and continuing to take the derivative of 0 gives us 0. Now let's move on to part B. In B, we're finding the second derivative because I specify that my n value is 2. So we're going to start by taking the first derivative. dy dx, that first derivative, is going to be bringing this exponent down in front. That'll be 4 times 3, which is going to give me 12, times x to the 4 minus 1, which is x cubed. What I did there is I did the constant multiple rule and the power rule all in my head. I left this 3 out in front, but I multiplied it by 4 as I brought it down, and then decreased my exponent by 1 to get 12x cubed. Let's do the next one in our head. Bringing that 2 down in front, 2 times 2 will be 4, and that'll be times x to the, decreasing my exponent by 1, would just be 1, so 4x. And then lastly, we're subtracting, well, the derivative of x is just 1. So if this is the first derivative, I'm now going to move on to taking the second derivative. So I'm going to take the derivative of dy dx, which gives me the second derivative with respect to x of, again, the power rule mixed with that constant multiple rule. I'll bring my 3 down in front and multiply it by 12 to get 36x to the, decreasing my exponent by 1 will give me a 2, so 36x squared plus 4x becomes 4 when we take the derivative, and this constant goes to 0. So 36x squared plus 4 is my second derivative. So now that we have a good understanding of higher order derivatives, taking the derivative more than once, multiple times, let's move on to what I think is one of the coolest derivatives there is, the derivative of e to the x. So if we have the function e to the x, that is the only function where the derivative is itself. So the derivative of e to the x is e to the x. That derivative of e to the x is e to the x, and it's the only function where this is true, with a few exceptions. Obviously, the derivative of 0 is going to continue to be 0, and the derivative of some constant multiplied by e to the x, remembering that constant multiple rule, we pull that constant out in front, take the derivative of e to the x, we're going to get that same thing e to the x with that constant out in front. So we're going to get the same thing again. But just remember that the function e to the x is the derivative of itself. So let's do example 3, part A to start. Looking at 2e to the x, well, rewriting this, if we're taking the derivative, f prime of x is going to be, remembering that constant multiple rule, we'll pull the 2 out in front, but we still have to take that derivative of e to the x, which we know is e to the x. So f prime of x is going to be 2e to the x. So again, that's that case where we get the same exact function, which I think is rather neat, because think about what the derivative is. That's the slope of the tangent line. So if we're on our original function, e to the x, whatever point we're at, the value of that function is also the slope of the tangent line. So let's move on to part B, our last part in this final example. We have y equals negative e to the x over 7. Again, we're going to use that constant multiple rule here. So our derivative dy dx is going to equal, I'll pull a negative 1/7 out in front before I multiply it by the derivative of e to the x, which again, the derivative of e to the x is e to the x. So this derivative is negative 1/7 e to the x, which is what we started with, negative e to the x over 7. So hopefully from this worksheet, you got a lot of really good practice with the constant rule, the power rule, the constant multiple rule, and that sum rule. So as we continue on in the next video, don't forget those, but we're going to learn a couple new rules, the product rule and the quotient rule. So stay tuned. And before continuing on to the next video, do a few more practice problems with these basic derivative rules. So until the next video, good luck with your online learning.